Now that we've talked a little bit about series and how to write out the terms of a sequence and then add them up, let's talk about a notation that can save us some time. In mathematics, we're all about new ways of writing things that kind of make things efficient and condense things, and a lot can be communicated from notation. So here we see this thing called sigma notation. Let's talk about what this is and how this relates to a series. Well, sigma notation can be used to simplify the writing of a series, and it uses this Greek letter that looks like this, and this is called a sigma. It is actually the capital sigma. There is a lowercase sigma that you see sometimes in mathematics. This is the capital sigma. In math, we like using Greek letters for things, and we've chosen sigma to represent the sum. So even though it looks like a backwards E, it's pronounced s, sigma. It sounds just like an S in our English alphabet. And so the way that we use this is we will take some sort of a sequence, or I should say a series, as we're adding up all the terms of a sequence, and we can take some u sub 1, u sub 2, u sub 3, and add those all the way up to some u sub n. This can take a lot of writing, but we can kind of condense this and package it into this notation here. And we would read this as the sum of, or this is the sum from k equals 1 to n of u sub k. So all of these pieces kind of are significant in some sort of way. We have the bottom number here is what the starting index is. So you'll see that this k matches with this k here. These are all the terms in your series. So when k equals 1, that means that we're going to be adding up u sub 1. When k equals 2, that means we're going to be adding up u sub 2. And when k equals 3, we're adding up u sub 3, and so on and so forth. So this just means that we're starting with the first term in our series, and we're going to be adding all these terms up in the series until I reach n. So if this read from 1 to n, this is like saying I'm adding up all the terms from 1 to, I can't remember now what number I said, 1 to 10. If n is 10, then I'm adding up all the terms from 1 to 10. This u sub k, all that means is these are just the terms of your sum. It's the way to generate all the terms in your sequence, and you're adding them up since you're looking for the sum. Now this is the terms of the sum, not to be confused with the movie Tears of the Sun, starring Bruce Willis. But this is a completely different thing. Let's talk about properties of sigma notation. There's some stuff that we can do with sigma notation that kind of manipulates things and shows these equivalences. If I have this summation from k equals 1 to n of these two different terms, a sub k and b sub k, I can also separate that out and say it's the same thing as the sum of that same two indices of a plus the sum of those same two indices of b. So it's kind of like you're just splitting up these two sums. And that should make sense. If I'm taking two certain things and I'm adding up all those terms over and over and over again, that's kind of the same thing as separating them out and adding these up and adding these up. Similarly, if I have some constant c and I'm multiplying that constant c times some term a sub k, I can kind of almost like factor out that c, and I can just multiply it by whatever that final summation is. And that should make sense as well too. If I were to multiply 2 times 1 plus 2 times 2 plus 2 times 3 plus 2 times 4, you're seeing here that I have this constant 2, and it's kind of like I have these terms 1, 2, 3, 4. And that's really the same thing as saying 2 times 1 plus 2 plus 3 plus 4, right? So this is the same thing going on here. It's like I'm factoring out this constant. And then finally, if I just have some constant being summed up from 1 to n, that's the same thing as just multiplying my constant by n. And again, that should make some sense. Let's put this in some numerical context. If I have the sum from k equals 1 to 5 of the number 2, right, that means I'm adding the number 2 up 1, 2, 3, 4, 5 times. So this is just going to equal 5 times 2, which is equal to 10. Since this means 2 plus 2 plus 2 plus 2 plus 2. This is like when k equals 1, 2, 3, 4, 5. So this is kind of how the summation, this sigma notation works. Let's use an example with sigma notation. So I want to expand this and evaluate it. Let's kind of see what's going on with the sigma notation here. So what I'll do first is I will kind of substitute in these different k values. This is going to mean that I'm adding up a total of 7 different terms. So let's just start by plugging in k equals 1, and we're going to work our way up to 7. So this is going to be 1 plus 1 plus 2 plus 1 plus 3 plus 1 plus 4 plus 1 plus 5 plus 1 plus 6 plus 1 plus 7 plus 1. So, on the bottom, let's just keep track of the k values so you can see what's going on here. So k is going to equal 1 for this term in the series. It's going to equal 2 here, 3, 4, 5, 6, and 7. So this means that I'm adding up all these terms in the form k plus 1 from 1 up to 7. So let's add these things up together now. So this is going to equal 2 plus 3 plus 4 plus 5 plus 6 plus 7 plus 8. And when I add all those things up, let's see, I get 10, 20, 30, and this is going to be 35. All right, so now what I want you to do is something kind of similar to that. Try this problem here, where you are using this sum notation, this sigma notation, and expand this kind of like we did in the first example, and then just add up all these terms. So pause the video and give this problem a shot. All right, and here's my solution. I end up getting 1/2 plus 1/4 plus 1/8 plus 1/16 plus 1/32, and when you add them all up, you get 31 over 32.